So I'm going to talk more, I guess, an overview of the Lattice spring model and sort of a bit more of a historical perspective, really. So I loved Yang's talk. It was pretty awesome, and maybe I'll elaborate a little bit on where the Poisson's ratio comes in. The sort of history of this really dates back to sort of the 1940s, and so some of the earlier work on what the framework method was, which, believe it or not, people used to solve lattice models by hand. So I'm very grateful that we have computers nowadays to do this for us. But the sort of the hierarchy, if you like, in terms of complexity of these models, the very simple models are often referred to as scalar in terms of the elasticity, but in terms of an electrical analog, they're referred to as the fused network models. And so there's been a lot of people who have looked at these. Essentially, there is no direction. There is no sort of force vector. You treat everything as just sort of scalar quantities. And these kinds of techniques are generally used to simulate, fracture sort of behavior and trying to probe sort of, the patterns of cracks and things. So here's a simulation where the damage accumulated in the material, and ultimately you got fracture along it. And this would be like imagining a network of resistors and having some of those resistors start to burn out. Right, that's the sort of the basic sort of type of model. The next sort of level is the Hookean spring model. And the Hookean spring model has an elastic energy, a Hamiltonian, written down like this. And this is very similar to the first term that we saw in Yang's talk just a minute ago. So the energy of the system is basically just depending upon the central force constant, the stiffness, the Hooke's constant, and then you just have the displacement. And then, it's only if it's in the orientation that the bond is oriented that that you get any energy, right? So it's only when you deform a spring in the direction that it's pointing. Now, obviously, in a Hookean spring, those springs can rotate around, and so in this model, the bond orientation will vary as you start to deform the system. And these are being quite popular, really, in terms of simulating a lot of sort of micromechanics, sort of simulating a lot of sort of systems that have, sort of inclusions and fracture mechanics and things like that. In terms of the sort of next level, maybe a sideways jump actually, is the Bom spring model. And the Bom spring model, again, has the energy that relies upon this central force constant, and it has the same term with displacement and the bond orientation, but it has an extra term, and this term is the non-central force constant. And basically what this means is you have a spring, and then any deformations sort of perpendicular to that spring are sort of penalized, if you like. So I can, if you have a spring in this direction, then deforming it in this direction will have a spring constant K, but deforming it perpendicular would have a spring constant C, right? Now, in this model, the bonds don't rotate, so it's not rotationally invariant. So if you have large deformations and part of the system is rotating as the crack is propagating through the material, then this isn't going to be able to handle those rotations. Now, it is possible that when you're mapping this on, and I'll talk about this later, when you're mapping these models onto linear elasticity theory, that you could envision mapping it in a rotated setting, and that way you still could have rotational invariance, but it would have to be done each iteration. You'd have to sort of minimize it, you know, with respect to that. So sort of mapping at each iteration as it rotates around, which might not be too dissimilar to the Hooke's spring model anyway, because the Hooke's spring model, you linearize it whenever you try to map it anyway. So it's but that's sort of the basic sort of Born spring model. Here's the typical force equation that you might get from this. And so in terms of the different terms, you know, this would be the force that's acting on a given node, and it's just sort of, it's related to the relative displacements of the nodes around it, right? Just like you'd expect from any spring. And the matrix then is just the matrix that contains all these spring constants. So for example, in the 1, 0, 0 direction, you would have the stiffness as you pull it in that direction, K, and then you have the stiffnesses perpendicular that try to penalize the rotation or movement away from that direction. Putting that into the rotation matrix, you can get it in any direction you want. So in terms of the 1, you know, the 1, 1, 0, it's pretty much the same. And you can map this on then, and I'll talk a little bit more about this later, but you can map on the discrete equations onto continuum elasticity theory, and then you can get things like the Young's modulus and the Poisson's ratio. Now, the Poisson's ratio, if you put C is equal to 0 in this, the K's will cancel out, and this is where the limit of a quarter comes in. It's a third in 2 dimensions and a quarter in 3 dimensions. So this is the limit in terms of, you know, how good you can get this to be, basically, in mapping your Poisson's ratios on. This is not a new problem. I mean, this has been sort of around for a very long time, and the earlier molecular dynamics simulations got around this with volume conservation terms, very similar to what Yang presented in his talk. So people have sort of tried to go beyond this limit. There's even been people have mapped on the spring model onto a displacement-based finite element method, and that way, basically, you're just solving the finite element method at that point. So there are more complicated sort of ways of writing these and getting more variations in those elastic constants. The sort of some of the basic ones involve things like this, where now you have the angle between 2 bonds. So you introduce 3 body interactions, and this could even, you know, this could either be the difference in the cosine of the angles or the difference in the angles, but it's just some way of penalizing, you know, 2 bonds that want to be at a given angle relative to each other, and then as they sort of move away, you want to sort of move them back, right? And again, you have to linearize this before you can map it onto continuum elasticity theory. There's a whole bunch of other work in terms of these beam network models as well. And the beam network models, they're actually getting quite complicated, but the very basic sort of idea was that when you have a beam, you can also have moments as well. So you have an orientation and things. So you can have sort of twisting of the bonds. But you know, again, a lot of them have multi-body interactions and things, so they can get pretty complicated. And what I'm talking about really is the basic sort of is the basic elastic model. Now, in terms of what you can do with this, then the first thing you want to do is, well, can you capture elasticity, right? And so here's a simulation from Stoszewski, where they were looking at solid particles. This is a very old paper, where you're looking at solid particles in a matrix. And basically, all you do is you remove bonds based upon some criteria. And this is some of the very early sort of fracture mechanics that were being done, with these types of models. Um, Here's a three-dimensional simulation of the inhomogeneity problem. So this is the the stress field in a more solid sort of spherical particle, and here's the strain field in the same particle, and we can sort of compare this to some of the theories. So in this particular work, the lattice, either the bonds are stiffer because they're in the particle, or they're more compliant because they're in the matrix. But we don't have any ones that are sort of in between. And so there's large discontinuous sort of issues around the sort of boundaries. You know, around here you start to get some noise. So this is comparing a whole bunch of different elastic fields to what you'd expect theoretically, but it's not really surprising because you're looking at a particle which is made up of blocks, right? So in terms of like trying to map on a continuous spherical surface with a bunch of blocks, you're going to get some kind of variations there. And again, you know, we can sort of continue this. Here's a microstructure of nanoparticles that are embedded in one phase of a diblock copolymer. So a diblock copolymer is basically a polymer chain that has two different types of materials. One is maybe, for example, more hydrophobic, and the other one's more hydrophilic. And so they try to phase separate and get away from each other. But then because they're tethered together, they can only separate so far. And then you can put particles in that want to preferentially sort of only be in one phase. So this way you corral the particles, and then it sort of gives it more of a stiff backbone. And so you can look at, for example, you know, here's the strain field in this system. You can see that having the particles, especially if you can align them in the direction that you're applying the stress, you can have a stiff backbone throughout the material that can improve performance, right? So they're getting that sort of mechanics from the microscopic sort of pattern. Now, a lot of people have been interested in plasticity in terms of in terms of its meaning. The sort of work that's being done on this, in terms of what I've done in the past, which is almost 20 years old now, but the idea is it's very it is very engineering, right? You sort of you know what kind of response you want, and so you tell the computer, this is what I want you to do. And so, you know, what you would do is, instead of having those nodes deform elastically, now you say, we recognize that the elasticity is going to get less, but we're going to have more deformation. So you put internal forces in there just to sort of shore that up, and then you reduce the elastic modulus to give you the correct sort of behavior. Now, this is using the Bom Spring Model. So you've only got particle-particle interactions, bond-bond interactions. So there's no volume conserving terms. So this is going to be limited to a Poisson's ratio of only a quarter. And obviously, you know, in terms of plasticity, you want to go all the way to 1, right? You want a volume conserving flow. So this sort of model would only really work if you had very small levels of plasticity, and you really need the volume conserving term to use this type of approach, which is, I think, what Yang has done, and we'll hear more about this later, I guess, in the in this workshop. But the what's really interesting, I think, is that the heart, and here's some more sort of just sort of mapping. I should explain on the left is the simulations. So this was just the simulation of the plasticity as it was forming, and then on the right was theory. So it was just sort of comparing it to the two. But it was very sort of mechanical, right? It was just you're just sort of putting it in. And one of the things that I always love about this type of simulation is that it's really mimicking what's happening on an atomic scale, right? It's basically saying on an atomic scale, you've got these sort of interactions that the Bohm model comes from modeling crystals. So you're sort of modeling something on an atomic scale and then saying, can we use that same basic structure and make it apply on a macroscopic scale to get sort of a micro mechanical sort of model. And when it comes to adding plasticity, I mean, all the approaches I've seen so far have all been along the lines of, well, we've just got to shore this up, right? We've just got to sort of make it so that the plasticity behavior emerges in a way that we sort of prescribe, right? But when you look at the microscopic origins of plasticity and the movement of particles, that sort of breaks down, and that's not something that is being captured, at least to my knowledge, in terms of these lattice models, because these lattice models are usually pretty structured. They're not usually things flowing around. And so I want to sort of come back to this point later on, but just to say that the plasticity in terms of these models has been fairly sort of rudimentary, right? There hasn't really been a lot of work done, at least that I'm aware of. You can also put viscoelasticity in, and this is sort of the similar vein, really. Here's the strain around a this is a clay platelet in a polymer matrix, and so the polymer matrix sort of when it deforms, it's a viscoelastic material, and so comparing different sort of rods and platelets and spheres and things, the idea was over time you would end up with reduction in stress, right? Now, to incorporate these sort of viscoelastic behaviors, then what you generally do is just put a dash pot in with the spring, right? It's really that simple. You're just sort of allowing the displacement to have two components. One is elasticity, and one is because of the sort of flow in that dash pot. So this is the sort of the Kelvin Voigt sort of model of viscoelasticity. Now people talked about fracture mechanics, and so here's a model where this is a polymer blend, so it's just two different polymers sort of blended together, and over time these domains would coarsen, and at some point you can imagine putting a fracture through this, right? And allowing the crack to sort of propagate through these different sort of structures. Now, in terms of this fracture mechanics, some people have done criteria where they've said that there's a critical energy, a critical strain, a critical stress. So there's a wide variety of different sort of ways in which people have tried to implement crack behavior in these models. In this particular model, it was a strain-based criteria, but what we did is we created surfaces and we had to remove multiple bonds. And the reason is if you consider, let's say we have a bunch of, it's like a two-dimensional sort of example here. Let's imagine we have a bunch of springs in our system, and we want to put a crack in between here. Then we're breaking a bunch of different bonds at once. We're breaking these ones that are in line like this first, and then we would break the diagonals. And what can happen in some of these models is that you start to get a small region where all the bonds in one direction start to break first, and then bonds that are sort of have a component in that direction will start to break later on. And it's just sort of it's a very unphysical kind of artifact, if you like. Creating surfaces does get around that a little bit, but even if you create surfaces, you're creating surfaces that are aligned with the lattice direction. So it's far from perfect, really, in terms of this. And one of the things that you really want to do is get random networks, okay, which I'll talk about in a second. Just to say that, in terms of the in terms of some of these fracture stuff, you can calculate things like fracture toughness and J integral and some of the things that engineering fracture mechanics like to see, even though from a physics point of view they might not always be the most best things to consider for your system. They're sort of the standard sort of things. So You can sort of get those out of these models too, which is something that you would more associate with finite element method. And then here's another fracture where now you have a relatively soft sort of matrix that can fracture around these sort of this sort of blob. It's like a zooming in, if you like, a fracture in one of those polymer blend morphologies. So there's been quite a lot of work on this. I've sort of moved away a little bit from lattice spring models for a little bit, but I continue to still use them. In one area, I was looking at aeroelasticity. So aeroelasticity is just how elastic and fluids sort of interact. And so we coupled the lattice spring model to a lattice Boltzmann model, where the lattice Boltzmann is a lattice model of fluid mechanics. And I love the lattice Boltzmann model for the same reason I like the lattice spring model, because it's building it on fundamental physics at the atomic level. You know, in lattice Boltzmann, particles on a small length scale, on an atomic length scale, are basically just moving around, bouncing into each other. And so what the lattice Boltzmann does on a more mesoscopic scale is it has these particle distribution functions that propagate on a lattice, and then when they hit nodes on the lattice, they collide, and then they settle down to this sort of equilibrium, or towards this equilibrium, and then sort of propagate on. So it's this propagating in collision, which is very similar to what you'd expect, you know, what happens on a microscopic scale. So, but here's a simulation of basically a ball with some fluid in it, and it's coming in. And as it's coming in from the right, and it's hitting the wall on the left. And so you can see initially the deformation of the elastic part, the lattice spring model, and the arrows inside of the lattice Boltzmann. This is the fluid mechanics sort of inside of this. And then, you know, as the sort of ball gets more and more deformed, all that energy is being transferred to the elasticity inside of that system, and the fluid is basically sort of starting to come to a stop, and so you're getting all these shock waves and things through the fluid, but eventually it sort of bounces back, and then you end up with a ball sort of bouncing in the opposite direction, right? And so it's sort of you know, this sort of simulations are typically done with finite element method, which can be really computationally expensive. And so using these lattice models, they're much more easier to use, right? And they're much faster. Another example of this is a simulation of a vein valve. So here the vein valve, the vein cusps, are these two sort of leaflets. And so in the body, the muscles around the veins, as they sort of contract, they push blood. But if they try to push blood sort of in this direction, then these sort of valve sort of leaflets, they sort of expand, and then they sort of they meet in the middle, and they stop the blood from being able to flow through it, which would basically be trying to flow it back to you know, the lower extremities or whatever. And then when you're flowing back up from the lower extremities, say back towards the heart, then it allows it to open up, and then the blood to flow. Right? And that's how the veins have unidirectional flow of blood. So it's just a nice example of this lattice spring model, again coupled with the lattice Boltzmann method, to get these sort of aeroelastic interactions. Now there has been some work done with random networks as well. Here's a model I did, which was looking at a random network in terms of the nature of the deformation. So the one on the left has more interactions, and the one on the right has less connectivity. And what you see is that when you have more connections, you have more stretching, and when you have less connections, you have more bending modes. So this is sort of a stretching to bending transition that you find as you change the number of connections in these types of network models. Now, this is a network model which basically you're trying to capture something that has this morphology, right? So you're not trying to capture the micromechanics of some elastic material. Now you're saying I'm simulating something that has a network structure. So for example, here's a picture of a simulation of Actin Networks, where basically what we did is we had the actin sort of exists as these sort of chains that polymerize on one end and depolymerize on the other, and sort of within a cell they're sort of moving around, and they form these sort of actin networks, which is kind of like the scaffolding of a cell. And this can kind of be important because, for example, in leukemia and things, you can have less, more compliant cells and things. So you have sort of damaging to this structure. But anyway, this is using a model where we coupled the movements of these actin sort of chains and then the elastic properties of the network as well. So we can change the parameters in terms of how much actin there is present, what the polymerization rates are, and things like that, and then couple it to the mechanical properties of these actin networks. But all of this work here is all because the network itself that you're trying to capture is inherently disordered, right? Now, one of the things I've been working on recently is trying to map a random network onto linear elasticity. And to my knowledge, there's not really been anything done in this regard. But the idea is, I would start with sort of the Lamy equations. And this is very similar to what Yang was talking about when we sort of map it on. What we're doing is we're comparing either the energy or the forces, and we're sort of making them match up between the network, the network of springs and linear elasticity theory. So in terms of linear elasticity theory, the Lamy equations are sort of well known, and they have sort of the Lamy constants, the displacements, the notation with the comma, and then the two indices just means derivative with respect to those two directions. The other Lamy constant, and then because I'm mapping on the Born model, this is not rotationally invariant, right? So there's an anti-symmetric term that has to come in order to allow us to map this on. And so there's a term in here which you wouldn't ordinarily find in sort of, I'm trying to think if Landau and Lifshitz has it in their book, because they do a lot of work on crystals, but it's something that is sort of required just because we don't have rotational invariance. But then you can compare that to the force in a lattice, right? And so here's the force. We have the we have the usual stiffnesses. We have the non-central force constants, which are penalizing sort of bonds moving around. We have displacement vectors, and then this is a unit vector that is in the direction that the bond is facing. And then to map it on, you would just do an approximation, right? An expansion of this, and then this is where you get the derivatives that you need to compare to the derivatives in the continuum elasticity theory, right? The Lamy equations I just showed. Now, when you do that, as you map each term, based upon which derivatives you're mapping, you start to get these equations out, right? And so here's just three. I mean, if you do this for two-dimensional systems, I believe it's like 21. And then for three-dimensional systems, I think it was 48. So you get a whole bunch of equations. But the the L here is the length of the springs. The E, this is just the unit vector of the spring, and then you have the constants of the spring, and you're summing them all up at each point in each node. You're summing up all around all those springs connected to that node, and then you're mapping it onto these Lamé coefficients that can then be used to calculate, for example, Young's modulus and Poisson's ratio. Okay. So here's some of the structures I was doing. In order to map this on, you do want some semblance of symmetry, just because if you had a system where let me just imagine a really idiotic scenario. So maybe you have something like this, and this node is only connected to bonds in one direction, sort of over here, sort of going this way. Then there's nothing pulling it in the opposite direction. So there's no way you could ever map that onto linear elasticity theory. You do need an even spread of these things to map it on. And that's why I've sort of chosen these sort of Delaney triangulations. The one on the left has an average connectivity of 6, and the one on the right has an average connectivity of 16. And the more connectivity you have, the more degrees of freedom you have to play around with those spring constants to map it on and capture the elastic behavior. So here's the residual, which is basically the sum of the square of all the differences between the theory and what we're getting from our network model, right? So how good are we at capturing this? So when we have a very low connectivity, sort of down here, we're pretty poor, right? We only have 6 connections. And I say we're reasonably poor. There's going to be some areas where you have almost like a perfectly triangular lattice, and that's going to match it pretty well. And you're going to have some areas where you don't, and you have sort of maybe sort of more of these sort of chains or bonds rather on one side than the other, and then you get sort of these sort of areas where the residual actually goes up. So this is sort of averaging it or taking it over the whole system, right? As you go up, though, it does get better, and you see that these comes down. One trick that I started doing is a spring is reciprocal, right? If you pull a spring, then every action has an equal and opposite reaction. You have the same force on both ends of that spring. But in terms of mapping this on, there's really no reason to assume that, right? Because we're just sort of building this model out of these two pairwise interactions just to try to make it as easy as we can. It doesn't really make it any more difficult to have different spring constants from either end. So I've introduced a non-reciprocal sort of spring. And now with connectivities of around 12, I'm starting to get really good agreement. And so now we're starting to get a completely random network recover linear elasticity theory for reasonable connectivity, right? I mean, I'm sure if I went up to like 24 or so, maybe with the reciprocal, it would come down, but because that would be like the equivalent numbers of sort of variables that I get to play around with. But in terms of systems, the non-reciprocal seems to work out pretty well. And so here's just a plot of the elastic modulus. And as you get sort of to higher connectivity, it's getting towards 1. This is the Young's modulus divided by the target. So remember, you set the spring constants based upon the Young's modulus and Poisson's ratio that you want to capture. And so the idea is you're trying to get to that. When you're solving a system and you only have a connectivity of 6, it's difficult to get to that. You're going to have some regions where it just doesn't behave properly. But as you have a higher connectivity, it starts to get there, and you get this region where you're close to 1 now, and it matches it pretty good. And the same with the Poisson's ratio. Again, the Poisson's ratio is limited because it's a Bom Spring model, but even so, you can sort of match on and sort of capture that, sort of like that. And so here's an inhomogeneity problem. Here's a particle of some stiffness, and the strain field, as you deform it, and looking at this, one-dimensional profile. When you've got 6 bonds, you do get a lot of noise, right? With the 6 bonds, which is this sort of red line, and the pink is the sort of error bars. The thing is quite noisy, because you do have local regions where you're capturing the elasticity better than others. But as you go up to higher connectivities, 16 was the highest, and sort of 11's in the middle. So even as you go to 11, it's matching up with the theory pretty good. Now, the theory in this plot is the theory calculated on the lattice. So it doesn't take into consideration the sharp interface. If I did, oops, so I'm jumping ahead there. This is just a fracture mechanics. Again, just removing sort of springs. But this is what I wanted to show. What you want to do is you want to capture where the particle interface is. So if you have a particle and it's sort of coming sort of around like this, this is just showing sort of one quarter of the particle, then you want to capture that much better than you do over here. And that's something that the finite element method has been able to do for many years, right? But it's generally not something that has been handled very well with the lattice spring model. Usually the lattice spring model is, you just assume that it's the same sort of grid size everywhere. But now, because we're mapping it on based upon just the local neighbors, it really doesn't matter in terms of the simulation whether you have more or less, right? So here's the stiffness. I'm just showing the stiffness now for these bonds, and you're getting sort of lots of little stiff bonds here. So sort of around this interface region here. And the benefit of that is when you try to do the same sort of inhomogeneity problem, increasing the density, and increasing it up to a maximum of 16 times. So sort of 16 times as many sort of nodes in that region right next to the interface. You can much better capture this interface. So maybe in sort of in terms of theory, it might be more precise, but in terms of what you're able to capture in the model, it's going to get better and better as you go to a much finer grid coming next to that. But this is sort of zoomed in. I mean, if you look on the outside, if you look at this, I mean, at some point, I don't know how much it really matters, how close you're getting at that interface. Now, in terms of the work I've been doing, so I kind of started it, and then I've recently got distracted, and so I thought I'd show you this. This is a gator, and I simulated the gator using the lattice spring model. So it's a 2-dimensional lattice spring model that is stretched over the model of a face, and sort of equilibrated. And then you can just see that because the way the 2-dimensional sort of model is sort of implemented, it doesn't penalize any sort of variations perpendicular to the mass, because fabric, you can sort of pull it and it'll stretch and stretch back, but you can generally bend it pretty easy. And so one of the things you find is you get all these folds starting to occur. And then through this mask, I'm using the lattice Boltzmann method, the fluid mechanics model I mentioned earlier, to simulate the airflow through the gator, and also sort of up as well. And so, this area here is where your glasses will get foggy. as you're wearing it, and sort of. So I got a bit distracted by that. But one of the things I sort of will leave you with, because thinking about, everyone's been talking about the plasticity, having a network which is no longer structured on a regular grid, but is able to be any sort of pattern you want. What we could do is have the nodes move and flow like they would in a plastic material, and then just remap that on to the new elastic behavior afterwards. And so I think some of this work with having the random networks could lend itself to sort of better plasticity in some of these very simple models. And then the plastic deformation itself would be volume conserving, because you could just move the nodes anywhere you want to be volume conserving, but the elastic behavior on top of it would still be confined, as long as you're always confining to two-bodied interactions. But I think, you know, to increase the complexity of the model, it kind of feels like at some point you might as well just use a finite element method, you know. And so I wouldn't know if doing that and mapping it on at each iteration is really worth it. So, but that's sort of my talk.